Now, does time exist at the most fundamental level? So the talk is rather general, and I think because we are not so many, you can ask questions at any time, not only at the end, so I can certainly give you more details if wanted and explain here. It's mostly non-technical, but of course I have put in a little bit of physics here. So I have prepared the following 5 sections. So the first is a very brief history of time from Newton to Einstein, and then we have to go beyond. I'll try to explain why we have to go beyond Einstein to understand time. And this has to do with quantum gravity, which is also my main field of research, the quantization of the gravitational field. So I spent some time to motivate this. And then, of course, the center of this is time in quantum gravity, and this gives you then already, I would say, maybe a glimpse of the answer to that question, whether time exists. And the last 2 sections, they give an application of all the ideas to the universe as a whole, to cosmology, because they're actually the most relevant concerning our own universe and its history. So it's quantum cosmology, and the end is then devoted to the direction of time, which is, of course, of utmost importance for our everyday life, but which is not covered here in these other sections. Okay, so modern physics starts with Isaac Newton, and you all know that he has pioneered research in gravity by suggesting this law of inverse, the inverse square law of attraction at the action of a distance. And for this to formulate so that every 2 masses in the universe attract each other instantaneously at infinite speed, of course, he also had to develop also just the concept of space-time, absolute space and absolute time, and this is pictured here. So I have here time vertically, and so this is 2-dimensional version of 3-dimensional space. And in Newton's concept, I mean, this is absolute, so you foliate the space-time, if you like, uniquely in terms of spaces. So whenever you have 2 events, it's clear whether they are the same time or not. So the earlier and the now and the later is absolutely given. So these are 2 world lines, 2 examples for motion. Distinguished motion is the one at constant speed and uniformly, where you do not feel any inertial forces, and this is a general motion, where you can also have rotations, for example, acceleration. So Newton writes in the Principia, so this is an English translation from the 18th century. Absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external, and by other name is called duration. And absolute space in its own nature without relation to anything external remains always similar and immovable. And it was these concepts that enabled him to formulate the laws of mechanics and the laws of gravity. Of course, there were already contemporaries who were posing these ideas, notably Leibniz, but also others, which Leibniz came up with notions for space and time that look more modern, more relative, and would fit much more into Einstein's theory, but at that time it was so general and was not possible to quantify it that he could not have an alternative to the Newtonian mechanics. I mean, to do calculations, celestial mechanics. This was the big success of Newton's theory until the 19th century, celestial mechanics. Okay, so let's jump to Einstein. So I said it's a very brief history. I don't talk about relativity too much, but Newton's theory of gravity lasted until 1915, when Einstein proposed his general theory of relativity. So what is the general theory of relativity? To have a short summary, so gravity is no longer a force acting at a distance. It is an expression of the geometry of space-time locally where the geometry is. So there's no instantaneous propagation. So you have three-dimensional space and one-dimensional time, unified with four-dimensional, in general, curved space-time. And this curved space-time has effects on all physical particles' fields, so it acts universally, because everything is in the universe with curved geometry. So this reflects the fact that gravity acts universally to all forms of energy, but it's much more evident in this geometric formulation than in a maybe kind of standard field theoretic formulation. Okay, so these are the Einstein field equations, just to put them down. I don't enter their discussion. Okay, 2 years later, he put his cosmological terms. That's where we today is very important. This is the day when he presented the final correct version. Now, the left-hand side is the geometry just mentioned of the gravitational field, and the right-hand side in this object he knew collects all possible non-gravitational degrees of freedom, which can be particles, fields, electrons, and be the standard model of particle physics with all this Higgs, and everything is here on the right-hand side. So everything covers to gravity. And the point here to emphasize is that space-time is dynamical. It's no longer the absolute arena that you had in Newtonian physics, on which the actors play. Now, gravity itself becomes an actor. That is, when I move around here, I create gravitational waves, which modify the space-time structure here in this room. Fortunately for you, it's too weak to affect you, but if this were a black hole, then it would be relevant. And I cannot, of course, resist to show you at least this one slide, because this was a major discovery, the direct detection of the gravitational wave in 2016, exactly 100 years after Einstein wrote his paper in 1916 about the existence of gravitational waves. You see, sometimes it takes a little bit longer to test physical things, although we knew here indirectly from pulsars that gravitational waves exist. But this was a direct test, so it's indicated here, and particular impressive here in this slide is that you not only have the gravitational waves, okay, so they are indicated here, and they match perfectly with Einstein's prediction, but you also have some other objects called the black holes that were also not there in Newtonian physics. Gravitational waves have no place in Newtonian physics because, as I said, you just have an action at a distance, and the gravitational waves, they propagate, so they are locally significant, where you have the curvature of space and time. And also you have these black holes, which is an object where the gravitational attraction is so strong that not even light can escape from it. So you can only see it by its influence on its environment, or if you have two of them that circle around each other and coalesce, they create a burst of gravitational waves. And this is what was observed. So this is in cosmic distances, so many millions of light years away, which means it happens many millions of years in the past. And then it reached us in 2016 to be observed. So this is a nice topic by itself, but for the concept of time, important is this background independence, which I have just mentioned. Space and time are dynamical. Time is not absolute and something is going on in space and absolute, but they interact with each other. Also with matter. So John Wheeler once said that space tells matter how to move, and matter tells space how to curve, or space-time. With the gravitational waves, one could also say space-time tells space-time how to curve, because it's just empty space-time that propagates. This is nothing material. It's empty space that propagates. Einstein recognized this maybe most important property of his theory very early. I think this quote is from the beginning of the 20s. So, okay, this is the original German, es widerstrebt dem wissenschaftlichen Verstand, ein Ding zu setzen, das zwar wirkt, aber auf das nicht gewirkt werden kann. So it is contrary to the scientific mode of understanding to postulate a thing that acts but which cannot be acted upon. And this is the old space-time, which is just there, and you can do what you want. The space-time is always there. But this was nothing. This was very unnatural in Einstein's thinking. And general relativity implements the idea that there is an action back on the space-time. The space-time has the same footing like the other, concerning this aspect, like the other fields and particles. So there are no absolute fields in general relativity. This has no background structure. So it's not like, I think this picture is from Roger Penrose, and the old idea is you have the fixed, in an old cinema, and the fixed screen, and you project the movie, and now you only have the movie but not the screen anymore. So everything is the movie. There are some other rotations that fit into the same, with this absence of background structure, this new way of thinking about space-time. So one by Wolfgang Pauli, one by Matthieu Bronstein. So Pauli, 1955, in Bern there was a conference, 50 years of relativity, which referred actually to special relativity, but if you look to the proceeding, it's about general relativity. And he was the head of that conference in Bern. Einstein had been invited, but he had died 2 or 3 months earlier before the conference took place. And in his closing speech, Pauli remarks, well, he actually summarizes all of the problem from his point of view. Also the problem that has to do with quantum gravity, to which I come. And he already formulated, as we would formulate it today, the main difficulty in quantizing gravity. It seems to me that it's not so much the linearity or non-linearity which forms the heart of the matter, because some people said, okay, Einstein equations, I did not tell that, but it's important that they were highly non-linear. This is why you have this interaction, also gravity with itself. The linear theory cannot do that. And when some people suspected that it's the non-linearity which makes it so difficult to combine gravity with quantum theory, but that's not true. You no longer have the Lorentz group, which is the symmetry of the background space-time without gravity, but you have this more general group which refers to the general coordinate transformations, loosely speaking. Already earlier, one of the pioneers of quantum gravity wrote the following. Well, as you know, I mean, he was in Soviet Union and had a very tragic death. I mean, he was one of the brightest persons, but with the age of 32 was shot in a Stalinistic camp. And he had not only developed the linearized quantum theory of gravity, but he also had made Gedanken experiments about the limitation of the classical concepts of space and time. I mean, it goes back to Riemann, that you have a smooth picture. Also Einstein had a smooth space-time. And he made Gedanken experiments showing that there are maybe small, discrete structures, whatever. He found out at that time that if you want to concentrate matter in very small regions, that something, a new object or a new situation arises. Now we call it a black hole, but it was clear to him that you cannot measure arbitrarily small distances, because these amounts of energy, they create, this event horizon that makes then a black hole and gives you a smallest non-vanishing distance. The elimination of the logical inconsistencies connected with this, with these experiments, requires a radical reconstruction of the theory, it means Einstein's theory, and in particular the rejection of a Riemannian geometry dealing, as we see here, with values unobservable in principle. These are the space-time points, because the point or point particle does not make any sense in Einstein's theory because it's a black hole. And perhaps also the rejection of our ordinary concepts of space and time and modifying them by some much deeper non-ending concepts. So this could also in German from the Grimm brother tales, wer es nicht glaubt, bezahlt einen Taler. Okay, so we have Einstein's theory, which is the modern theory still of gravity. It's in accordance, as far as we know, with all existing observations and experiments. There could be some that point into a new direction, but it's not clear. So far, it's at least possible that everything what we observe, even the dark matter and the dark energy and the like, is in accordance with general relativity, and it has entered daily life in the form of the GPS and the like. So there you have to implement Einstein's equations, because you have these light rays in the vicinity of the Earth that propagate, and the satellites of the GPS. And if you put in Newton's equation, then you do not find your way here, because then within a day you have kilometers of error. Already this is a test of Einstein's theory. Now, so why do we want to go beyond? Because I talk here about quantum gravity, which is the quantum principle, which quantum theory is relevant usually for the microscopic, and it's the most successful theory in terms of experiments and everything, because everything that has to do with atoms and nuclei and molecules and particles is described by quantum theory, quantum field theory. So, except for gravitation, which is a classical theory, Einstein's theory, and so this is our experiment. So concerning the experimental and textbook level, we have these two frameworks: the classical Einstein theory with space-times and so on, and trajectories, and quantum theory with probabilities, wave functions, and all the like. And so I want to argue here that actually this cannot be the final state of affairs. So that there is a region where both of this is important, that actually quantum theory should be applied to gravity like it's applied to other interactions. So this is maybe not even a complete list of motivational points, so I will explain this in the next slide, what I mean here. The superposition principle, with this deep principle of quantum mechanics, which states that if this is an allowed system of quantum state, and you have another one, you can add them up and you still have an allowed quantum state. Then the unification of all interaction, which is the idea of the program of reductionism, which was successful in the history of physics, that hitherto, disconnected physical theories were discovered to be aspects or limits of the same underlying unified theory. And so here you see, if I may here go back, this here on the right-hand side, the non-gravitational field, they're all described by quantum theory. So in these Einstein equations, of course, they cannot be correct, because in quantum theory means you have to put your wave functions and whatever. You cannot have it in a classical way. Of course, you could somehow modify it and still have it, but it would be unnatural or a bit bizarre to have a fundamental theory where you have one piece classical somehow and all the other pieces are quantum. It would somehow be against our intuition of a unified theory. So this is then the idea. If you have unification, then you should have one framework. And because the majority is quantum, and the most successful would be naturally have quantum theory of gravity. Also, Einstein's theory is incomplete, and it's intrinsically incomplete, not like Newton's theory. So you can, within Einstein's theory, prove theorems, the singularity theorems, proven by Hawking and Penrose and others, that say that under general conditions, the theory breaks down when it comes to certain situations. And particular situations are the interior of the black holes, and we have seen that they exist. But we do not really know what this is. Maybe I moved too much around. So we don't know really. Interior exists. So the Einstein theory breaks down in the inside because it produces regions of infinite curvature. Also, the Big Bang, which stands here for the beginning of the universe, times zero, if you like. Also, this is outside Einstein's theory. So either you say, okay, I don't care, or as the physicists do, if they want to understand, you want to enlarge the framework to understand this. Okay, the problem of time, this is the aspect that is the most important one for this talk, so I will not really talk too much about these other things. And I will discuss in detail, but in brief it means that quantum theory and gravity have totally different concepts of time, which is also not an acceptable state of affairs for a fundamental theory. And the pragmatic reason is that alternatives have been presented to quantum gravity, but they are not really viable. Whatever you find, they have some problems, or it looks ugly, or has even some experimental problems to have a classical gravitational field coupled to quantum. So the first point, superposition principle. So let me only quote here Richard Feynman. So 57 was 2 years after that Bern conference. It was another important conference in Chapel Hill in the United States, where all the major figures of the time were present. This is the conference where I would say the real quantum gravity research has started, because they were all there, apart from Feynman, Wheeler, DeWitt, Meissner, Bergman, and many people. And if you go through that proceedings, also the discussion you can read, then you see they treat all the problems. So Feynman has the following Duncan experiment. So you have a beam of spin 1/2 particles, so it's called a Stern-Gerlach type of experiment. So these are quantum systems that, if you have a magnetic field, you can have two options, either spin up or spin down. And say for an electron, and if spin is up, it will be deflected here, and if spin is down, it will be deflected here. But now comes the superposition principle. You can superpose up and down, and this is something new. It means either here to the right or to the left. So it's not just a collection of ups and downs, it's something new. So quantum theory by interference can create that. And so if you have this up and down, then you have a superposition of the two. And now, so this is the standard textbook thing, and new is here that Feynman envisages this be coupled to a ball of macroscopic dimensions, so that if spin up, the ball is deflected upwards, and if spin down, the ball is reflected downwards. But what happens now when you have the superposition? It means the ball is in the superposition of being deflected upwards and downwards at the same time. So this is a different version of, say, Schrödinger's cat, where you have a superposition of some macroscopic system in being simultaneously in the same states. And this is why then Feynman argues, okay, the ball has a gravitational field. You can measure gravitational attraction, and also the field is in a superposition. It's simultaneously like that and that. And so you need for this situation, you need a quantum gravity. If you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. It may turn out, since we've never done an experiment at this level, that it's not possible. There's something the matter with our quantum mechanics when we have too much action in the system or too much mass or something. But that is the only way I can see which would keep you from the necessity of quantizing the gravitational field. It's the way that I don't want to propose. Of course, there are some alternative suggestions, notably by Roger Penrose, who says that as soon as gravity comes into play, something really radically new happens. So this superposition just breaks down and collapses to one of the two, and the world is classical again. Maybe, yeah, but it's certainly not something that is seen so far, and it's in contradiction to our ideas about quantum theory. So once you have maybe accepted that there are some reasons to do quantum gravity, of course, then the problem is to construct a theory of quantum gravity. And I can already say now that we have not yet reached that stage, although the first papers have been written in 1930 about this. It's long ago. John Wheeler once remarked, no question about quantum gravity is more difficult than the question, what is the question, or what is the approach? And here we are, of course, entering a conceptual and also philosophical regime about what is the meaning of all these concepts that are used, maybe naively used sometimes in phenomena, but do not have maybe an immediate meaning. So what are the main approaches? Certainly the most conservative is to take Einstein's theory and apply quantum rules, standard or new quantum rules to find the quantity of gravity. This gives you a quantity of the gravitational field. It's not yet unification. This is what was first started in 1930, and depending on how you do it, I can, if you wish, later explain more what this means, but this is two different methods. And Rosenfeld, Leo Rosenfeld, in 1930, he pioneered actually both of these. So he was the first who used these covariant approaches. So maybe you have heard about concepts such as path integrals and others. Or you use the so-called canonical approaches, which I will focus my discussion of time because there it's most transparent. This means that you take the metric, I should say, the geometry is described, Einstein divided metric, which gives you the space-time distances, and you apply quantum rules. You make out of it a quantum variable, have wave functions for it and the like. You can do it with the metric, but you can also do it with new variables that were invented by Ashtekar in 1986. They are called connection variables because connection is a mathematical concept, and it's also used in Young-Mills theories, which describe quarks and leptons and the like. And if you use connections, then it looks gravity looks similar to those other fields. And this was the motivation for him. Out of this grew the loop quantum gravity approach, which is also the connections but integrated around the loop. So it's something more non-local. String theory is much more ambitious. String theorists claim that, okay, this is not sufficient. You should start from a quantum theory of all interactions, not just gravity. You have a fundamental theory of everything, as they call it. I'm not so sure these days, out of which all the various dynamical fields and interactions like gravity or electromagnetic dynamics emerge. So in a sense, gravity is emergent in string theory. It's not there at the fundamental level. Whereas here it's there fundamentally. Now you have these other approaches. Typically they have some fundamental discrete structure, and here are some names. Quantum topology calls a set group field theory that partially have grown out of the other approaches, partly have constructed by themselves. But I will not enter them. Yeah, I will go to the canonical quantum gravity. So this is a slightly more technical, but I will explain the features. To understand what time means in quantum gravity, of course, we have to say something about the framework of quantum gravity. And the central equations of canonical quantum are so-called constraints. What is that? This was the work of Louis de Broglie in France. And Schrödinger was asked, you claim that there are these wave aspects. What is the wave equation? Write down an equation. So in his Christmas holidays, 1926, 1925, 1926, in the Swiss mountains, he found this equation. And he did it in the following way. So he was very good in optics, Schrödinger. This is what he was trained. And so he recognizes that the relation between mechanics and quantum mechanics, but the not for quantum mechanics is the same as the between geometric optics and wave optics. So we could just rewrite Newton's equation in a form that they look like the ray optics equation, and then he guessed a more fundamental thing that corresponds to the wave optic. But now not applied to light, applied to all forms of matter. This was the Schrödinger equation. So he, in the English translation, he wrote, "We know today, in fact, that our classic mechanics fails for very small dimensions of the path and for very great curvatures. As this failure is in strict analogy with the failure of geometrical optics. That becomes evident as soon as the obstacles or apertures are no longer great compared with the real finite wavelength. Then it becomes a question of searching for an undulatory mechanics, and the most obvious way is by elaboration of the Hamiltonian analogy on the lines of undulatory optics." So you have, and often this is done in physics, that you don't just invent things from out of the blue, you have analogies. And you extrapolate these analogies to the new realm, and you then define something new. And Schrödinger did this by having this optics analogy to all forms of matter. And this is why he could find his wave equation. Now let's ask, why did I put this here? You can do the same thing for Einstein equations, not just for mechanics. You can rewrite Einstein's equations in a form where it would correspond to this geometric optic limit, and then you can guess and devise a wave equation that gives back this Einstein equation in what we call a semi-classical limit. And this is, okay, Dirac and others, Bergman already worked on it, but it's mainly due to these two gentlemen who were also present in this 1957 meeting, John Archibald Wheeler and Bryce DeWitt, and they did this in the 1960s. And the result is called the Wheeler-DeWitt equation, which is still one of the most conservative equations to quantum gravity, because, as I just said, it just applies Schrödinger's procedure to Einstein's equation. And this is then what you get. You don't invent new things and new concepts. And so you see you have then equations h psi equals 0. I can explain later after the discussion, if you like, these formal things. But say for the main talk, it's not needed. What is needed is that there is no explicit time anymore in this equation. Now I should have maybe written down Schrödinger's equation. There you have, but I can write it down here. Yeah, Schrödinger's equation, you have this h on the side, then you have not 0, but you have a derivative of this with respect to time. And this here is Newton's absolute time. This is what you have in ordinary quantum mechanics, but this is absent here. So there is no time anymore. So this is already, you see here, the question, the title was, does time exist at the most fundamental level? And here you find a fundamental equation that has no time. So you see here, we would now think that the answer is no, and there is no time. But can you believe that? Maybe you are shocked, or you don't believe me. Well, John Wheeler has explained the reason for that, and here on the blackboard, I could also use this blackboard. So he gives an analogy with mechanics and quantum mechanics. So in mechanics, you have a trajectory, or you can talk about trajectory of a particle going from here to here. Yeah? This is what we do, a succession of positions. But in quantum mechanics, the trajectory is gone. There is no trajectory in quantum mechanics. There's a wave function that depends only on the position, and that gives you an amplitude for that position and a probability. This is indicated, although there's no trajectory anymore. But of course, in quantum mechanics, still you have this Newton's absolute time. In addition, outside is there. Now, in Einstein's case, there is no absolute time anymore. There's just space-time. And the space-time is, in fact, the generalization of the trajectory. It's a succession of spaces. So, if we apply the quantum rules here, then just doing conservative quantum theory, it would mean that the space-time vanishes in the same way as the particle trajectory vanishes. This is what Wheeler and before him even Dirac clearly formulated. That space-time, if you believe into this standard one, can no longer be a fundamental concept, and only the spaces remain. And you see, time is gone. Time is gone. Okay, here's the problem of time. The other problem of time, if I speak too long, you will take care of. So the external time t has vanished from the formalism. This is the most important message from here, even if you don't understand what is in the calculation. But I think the picture should be clear. No? If the trajectory is away, then also the space-time is away by the same methods. This also holds for loop quantum gravity. So you should not think this is a particular property of the Wheeler-DeWitt equation. In fact, it holds for any theory that has no absolute time at a classical level. So whenever you have a classical theory that has no absolute time, like Einstein's theory, you can have generalizations of Einstein's theory. The quantum version has got rid of time. The Wheeler-DeWitt equation, if you look more carefully, which I have not done here, has a structure of a wave equation in the sense like an oscillating string, like a string, and there, of course, this equation has a structure that distinguishes between space-like and a time-like variable. And this is true also here, but this time-like variable that emerges in this way is constructed from space. So in a sense, this is like in the astronomy when you have ephemeris time that you use from actual positions of objects. Construct time. This is in a sense what it corresponds to, because there is no time apart from this intrinsic time. I perhaps will not enter this much, but for those of you who know, in quantum mechanics, of course, we have this probability interpretation, and for this we have a certain mathematical structure, which is the liquid space structure, and we have the probability conservation, but this is in time, t. When we have the time, we talk about the conservation of probability. But what happens if time has gone? Do we still need that? What happens with this in a timeless situation? Now, semi-classical approximation. Of course, this is a candidate for fundamental theory, but of course, to recognize the significance, we must be able to make a bridge to the known physics. Because we know that time is, and you wonder how long this will take here and so on. So time is, of course, a good approximation, at least. So how do we get it back? Now, in this approach, compared to other approaches such as loops or strings, it's easy because it was constructed in this way, the relativity equation. And more formally, you can derive the limit that you have quantum theory in a given external space-time. This is a technical procedure known from molecular physics, what von Oppenheimer in 1929 did. There, they could treat a system of nuclei and electrons in a very convenient way by recognizing that the nuclei are much heavier than the electrons. And here, in a sense, the gravitational field is much heavier and slower in the equation. And so in this way you can find or recover a semi-classical time, a WKB time. So if you recall, we have this trajectory, which in Einstein case corresponds to the whole space-time. And so this is such an object is found again in this limit. And you can then identify that this time by having the parameter that goes along this. So like in the geometric optics limit, then you have recovered a light ray from the wave optics. And the wave optics, there are no rays. So in full quantum gravity, there's no time, but in this limit, which is, these are technical terms, but it's a kind of geometric optics limit, you have the time. And then you can recover this thing as an approximate equation, but this is no longer the absolute thing that is always there. It comes, in a sense, from this timeless equation by having a certain psi that allows you to do that. So you can, in this limit, the standard formalism of quantum theory, the standard probability interpretation is recovered as an approximation. And you can go to higher order terms, which we, for example, have studied, but I will not enter these. We just mentioned that the relevance of this can also be applied to observations. So this is a famous picture, the cosmic microwave background spectrum, the anisotropies from the Planck satellite mission. So perhaps you know we have this cosmic microwave background radiation that is everywhere, also in this room. It's approximately uniform, but you have small anisotropies, and they are the seeds for the structure formation. They come from the early universe, and according to our current ideas, they come from quantum fluctuations in the early universe. So to understand this, some quantum aspects of gravity have to be used. But this is the limit then where this semi-classical time has already emerged. We have not yet a direct window to these timeless worlds, and probably we will not have ever a direct limit to the time and the space of the universe. So let me then come to the quantum cosmology. So then the last two parts. In a sense, it has already started with Georges Lemaitre in 1931, although this was not done at the basis of quantum gravity, but he had the idea that he was the father of the Big Bang, so he thought, okay, the Big Bang, then everything is small, and then quantum theory should apply. And so he wrote, if the world has begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. If this suggests it's correct, the beginning of the world happened a little before the beginning of space and time. Now this is a little bit ironic, because what does it mean it happened before the beginning of time? Maybe philosopher can explain, but yeah. So, but at that time, of course, Georges Lemaitre did not have a formalism for that. He had this idea of this quantum, but I think precise equations only come later with the relativity equation. So this is now only one example, so that you see. I can explain the details, but they're not important. So this is a cosmological example of the relativity equation, H epsilon 0, where you only have 2 degrees of freedom. The size of the universe, which is A, the so-called scale factor, and this chi is a matter degree of freedom, because the universe is not empty as matter. So this is a homogeneous universe with homogeneous matter. And you can quantize it and have a relativity equation, and you can solve this, because this equation is rather simple. So this is the wave-vector solution psi over A and chi, okay, some years ago I investigated, and you have classically you have this Lisa-Shu ellipses, and here you can now construct wave packets that follow these ellipses. So what I want to say with this picture is that you then can apply standard quantum ideas to relativity, where you can do what the quantum theorists do in atomic physics, for example. But now you do it with the whole universe. So this is an important point for the understanding of time. So let me explain it carefully, because it has really a bearing also for what I call here the concept of determinism. So in the classical theory and the quantum theory, they are totally different. In the classical theory, so classical cosmology, so this is the size of the universe, this is a matter degree of freedom, and I take here a model for the universe that classically expands, has a maximum and recollapses. It may not be the realistic model nowadays, but it's still a possible model. So if you, for example, give here initial condition, then it expands, has a maximum and goes down. Okay, you could also start here, because there's no absolute direction. But once you start here, it's clear that this recollapsing universe part is the deterministic successor of this expanding one. And if you do it on a computer, you see how it goes. This is what I wrote here. But how do you do this? Do this in quantum gravity. There is no trajectory. There is just a wave function on the space of A and phi. And if I want to have a wave packet that's like here, then I must, that follows here, I must solve the wave equation. But the wave equation does not proceed along a trajectory that does not exist, and it proceeds actually from small a to larger a. The mathematicians call it the hyperbolic equation. And so to have a wave packet along, you must put this as an initial condition, here one and here one. So this is for the wave equation and for the intrinsic time. This is the initial state. Now, otherwise, you get just a total mess. You don't see the classical evolution anymore. So in a sense, the recollapsing wave packet must be present initially with respect to the initial condition. And so this is certainly totally different from this idea. And as a consequence, there's no intrinsic difference between the Big Bang and the Big Crunch. They are the same in this configuration state. This is important for the understanding of time and the absence of time. Yeah, maybe I skip the singularity avoidance or just say a few words, because I mentioned earlier that there are singularities in Einstein's theory for the Big Bang and the black holes, and now one can investigate whether they are avoided, for example. And in fact, they can. I mean, one has to impose certain criteria, and one would be that to see whether the wave function, say, is just zero at the region where there classically is singularity. Because if the wave function is zero, then heuristically you assume that there's a zero probability for this to occur. You cannot just reach it. The wave packet will disappear before you enter it. Or that the wave packets just spread out and there's no classical singularity. So the point in both of these is that the semi-classical time comes to an end, and you can no longer talk about approaching the singularity. So this is how it's solved. Yes, it's just outside the classical accessibility. This is one example that with my colleague Sasha Kamenchik and my then student Barbara Sandhöfer calculated that this is the classical trajectory, and you have a singularity here that you find a solution that really goes to zero. So this classical singularity is absent here. So you could think about a universe that evolves there, but everything disappears before you come to this, including the observers. This is maybe quite a popular picture coming from Stephen Hawking, and uses a different language with path integrals, but in a sense it's just a different language for what I explained now. And for him, when we go back in time to the Big Bang, I mean, time becomes like a fourth space dimension. So there's no longer a time evolution. So the beginning of the universe is smooth like the pole of the Earth. There is nothing singular there. And this is because time, which is evolved, only later comes real time. In this way, before that, it's just absent. Okay, he calls it imaginary time, whatever it is that is, but you can also call it's the absence of time. So this model, for the first time, we presented at a conference in the Vatican of '82, the appropriate place for discussing the beginning of the universe. And he said there ought to be something very special about the boundary conditions of the universe, and what can be more special than the condition that there is no boundaries. And this is what is known as no boundary condition. Those who have heard about quantum cosmology know the no boundary conditions, Hawking and Hart, but first proposed here by Hawking here. So this conference proceeding is certainly very interesting, because there's also a preface by the Pope, and who says that, okay, he welcomes everyone to write scientifically about the universe, except for the beginning. It should be really special, restricted to the church, to the religion. And Hawking just did that. And also, unfortunately, the Pope, in his preface, he also polemizes against Lemaitre, without mentioning his name, saying that you should never talk about this single quantum and so on. So he was also not happy with Lemaitre, who was a Catholic priest. We don't know it. Who said that? But it's just a side remark. So how much time would you give me until 4 o'clock?
You have 5.
Yeah, you have 5 minutes, also roughly. So I mentioned this problem with the superposition, and also when you have a quantum theory of gravity, you can have superposition of macroscopically different gravitational fields, also different universe at the same time, which we do not observe, but maybe it's relevant in the early universe. But there is a procedure that is well understood in quantum mechanics called decoherence, that gives you an explanation why, even if you have such Schrödinger cat states, you don't see them, because they're in interaction with their environment and therefore are invisible. And so time only can emerge, of course, in this sense just mentioned, if you have avoided the superpositions, because if you have the superpositions, they all will have a different time by itself, but a superposition has no classical time. So you should be able to understand that they are separate. And this is what the decoherence makes. So this is an analogy again. You see, analogies are important from molecular physics. The emergence of chirality. So you have in the Schrödinger equation, there's no difference between left and right. So, but we know from Sugar and others that they have a spatial structure which is not identical to the mirror image. And in principle, you would have a superposition of the two, because the superposition is the same as the mirror image, because at the same time the right and the left. And the point is that the interaction with gas molecules who scatter carry information about this superposition away. They're still there, but they're away, and you don't see it, and you see then a right-handed or a left-handed molecule. Depends on the size of the molecule. For some, you see the superposition for the very small one. And the same is in the quantum cosmology. We have these superpositions, but unless you are in very early universe and so, you have this decoherence. And you can understand why today, when we do modern cosmology, we don't have to face the problem of superpositions. It looks like a classical universe. No? And also, this happens for the structure in the universe, because according to our current ideas about so-called inflationary ideas, as said, they come from quantum fluctuations, but it's not what we see. And you have to understand how out of this quantum fluctuates and the quantum superposition, the classical structure in the CME comes, out of which galaxies have grown. And okay, this is a famous picture from the Hubble telescope, but for example, we had some time ago also investigated how really this can be understood in quantitative detail. And the fascinating thing is then to see how the very small, the quantum, here unifies with actually understanding of the macroscopic structure in cosmology, the galaxies. The interpretation of quantum cosmology here, I said, both quantum general relativity and also string theory preserve this linearity, so they have this superposition principle. So even if string theory is very complicated mathematically, but extremely conservative concerning the quantum aspects. And so they all have these superpositions. And the only interpretation so far that we have is what is called the average or many worlds interpretation. So there are all the possibilities exist in a philosophically, I don't need that to discuss, sense of existence. And but we don't see these other worlds because of decoherence. So Bryce DeWitt already very early has emphasized that in his pioneering paper. Average view of the world is a very natural one to adopt in the quantum theory of gravity, where one is accustomed to speak without embarrassment of the wave function of the universe. So this is, of course, that you cannot imagine how radical this at that time was for persons who could imagine wave functions only for the atoms at that time. So it was not, unless you had a maybe permanent precision in early years, you could not mention these ideas without being maybe becoming at some danger. Yeah, the direction of time, maybe I can be very short and even do this in the time allocated. So here this is a painting that symbolizes the importance of the arrow of time, which I have not yet mentioned. So far there was no direction, it was just a time parameter. But in our world, of course, we experience this passage of time, like here in the Cézanne painting, where you have this grain and the fruits and so on that die down. So how comes this direction of time? I mean, that we remember the past but not the future and so on. And this was always a puzzle, because before quantum gravity, I mean, all the equations, they were symmetric under time reversal. So classical mechanics, you can move in this direction or in this direction, and the wave function here propagates in this time or that time. So where does this come from? I mean, of course, we have one law, the second law of thermodynamics, that expresses that, but this is a macroscopic law, and we would like to have a microscopic foundation. And the only way out is to have a very particular initial condition in the world, because otherwise you cannot understand this direction. because then we would expect we are in thermal equilibrium, or that we have influences from the future, whatever. So only if we imagine that in our universe we have a very particular initial condition, out of which we then have the error of time. And this was already, written by Boltzmann very early, in end of the 19th century. Of course, the question is about initial condition. Yeah, when you look around, we have, of course, the stars, we have the sun. We don't have everywhere an equilibrium, so we have really a distinction between the stars and the empty space. But where does the sun come from? Well, gravitation is the stability of dust clouds, and this points to cosmology. So we can only understand the error of time if we understand cosmology. And this comes back to this initial condition, for which we need quantum gravity, for which Einstein's theory is insufficient. So you see how this is connected. So Boltzmann at that time wrote that in nature the transition from a probable to an improbable state does not happen equally often, as the opposite transition should be sufficiently explained by the assumption of a very improbable initial state of the whole universe surrounding. Of course, at that time there was much less known about cosmology. The world was assumed to be static and eternal. And so Boltzmann had to assume that, of course, he was the pioneer of statistical mechanics, that there are these fluctuations, that an improbable state can suddenly appear with, of course, extremely small probability, but in an eternally existing universe, it always happens at some point. So for Boltzmann, it had happened in the past, and now we are going from this improbable to probable state, and there we are. Of course, now people know the universe is only 14 billion years old, so we have other explanations, but we have explanations in principle, and this is one of the last slides now, that you can, from the relativity equation, at least in principle, understand where this comes from. Okay, the relativity has no time, so how do you understand the error of time if there's no time? The relativity equation gives you a certain structure for the size of the universe, and it enables you to have a very special initial condition for the universe that is very simple, and that if you put this in, this wave equation for bigger universes, you have, in a certain sense, a growing of entropy giving a direction of time, which would only point from a small universe to a large universe. So you could never see a recollapsing universe, because time comes from having a special initial condition for vanishing size of the universe, and then you have increasing complexity pointing from a small to a bigger universe. In this sense, it would then define the direction of time. The size of the universe would define the direction of time, and the expansion of the universe would perhaps then be called a tautology. Yeah. Okay, so this is my last slide, and to be time, well, 2 minutes. So just 2 quotes from the pioneers that reflect the situation, John Wheeler and Bryce DeWitt. John Wheeler, 1968, these considerations reveal that the concepts of space-time and time itself are not primary but secondary ideas in the structure of physical theory. These concepts are valid in the classical approximation. However, they have neither meaning nor application under circumstances when quantum geometrodynamic effects become important. There is no space-time, there is no time, there is no before, there is no after. The question what happens next is without meaning. At a fundamental level, I think we have a certain idea what happens next. There will be some coffee at some point. But fundamentally, this is what happens. And Bryce DeWitt emphasizes that one learns that time and probability are both phenomenological concepts. Phenomenology here in the sense of the physicists that are non-fundamental. Not like Husserl, but they are, so in a sense, derived. But you can derive them in the macroscopic situation. Okay, I think I have now given you, I hope, that comprehensible, at least a red line of ideas. Of course, it was done in a particular approach to quantum gravity, and as I said, there's no yet the consensus about what is correct. This here has the big advantage that it's the most conservative and I would say conceptually straightforward approach, because you just do apply what you do in other situations. You assume the universality of quantum theory and that the superposition principle is universal. So you want to keep as much as possible of the structures in the physical field that you have, and without having many new dimensions and whatever. And this leads to this picture. So this picture is amazing, no? This absence of time, and it has also relevance for our universe and for our understanding of the universe. So it's clear that if this straightforward quantization is correct, the consequences are there. Whether, of course, our final theory at some point is this or something completely new, we don't know. Thank you.